Today we have Professor Bo Chiu from University of Hawaii giving a talk on the regime shift of the Kuroshio extension system after 2018. And thanks to Bo for presenting the seminar at 6 a.m. his time. Bo, the floor is yours.
Great. Okay. Well, thank you, Tony, and everybody for joining. And it is my pleasure to present this seminar. Just want to start by acknowledging my collaborators, Shui-Min Chen from University of Hawaii and Eitaro Oka from Aori, the University of Tokyo. And so now, since we have a 30-year worth of satellite altimetry data, so we can start to look into sort of the mesoscale versus larger scale ocean variability in the world ocean. So this shows the RMS sea surface high amplitude variability, sort of in the mesoscale range, so shorter than, well, annual to mesoscale variability. So if it can, let me see if I can point to. Yeah, so in the Kuroshio extension in the Gulf Stream region, you have sort of a very comparable amplitudes of variability. However, if it goes to the longer time scale, so anything beyond the 2-year time scales, now you see a somewhat a different picture. The Kuroshio extension seems to have a higher fluctuations than the Gulf Stream. And obviously, so the question is what kind of a sort of a long-term interannual decadal variability we are seeing. So this is just a one manifestation of what's happening in the Kuroshio extension. So what's plotted here are the path of the Kuroshio in this northwestern Pacific box, showing the axis of the Kuroshio in every 2 weeks in different years. So as you can see, in years were indicated in red, when the Kuroshio extension are relatively stable, and whereas in the in blue years things are quite unstable. And so this is from 1993 to 2017, prior to this regime shift I will be talking about. And you can obviously be more quantitative. So this is one measure by integrating the path length from coast of Japan to 153 east. So you can see the alternation between short path versus fluctuating and a relatively long path, so stable as compared to unstable years. And there are other dynamic quantities you can use. The blue curve here shows the strength. So this would be the sea surface height across the Kuroshio extension jet, zonally averaged from 140 to 160 east. So as you can see, when things are stable, you have a relatively greater, stronger eastward jet as compared to when things are unstable. And the third panel here in pink shows the position, the zonally average position of the Kuroshio extension jet. So there's a tendency for the Kuroshio extension to be shifting northward, where it is stable, and southward when it becomes unstable. And finally, the last panel here shows the intensity of the recirculation gyre. So basically, it's the sea level anomaly averaged in the box south of the Kuroshio extension jet. So the recirculation gyre again is stable. Sorry, is intensified when the jet is stable. So, so this is just visually comparing the two states, unstable versus stable. So since these properties, dynamic properties, are similar, so in about 10 years ago, we came up with this Kuroshio extension index, K index, which is simply the arithmetic average of these 4 dynamic properties. So let's define a positive index means a stable state, and a negative index, unstable state. The good thing about introducing this index is you can conduct a regression analysis between this index and the sea levels everywhere in the Pacific Basin. So this is a result showing here. Essentially, when the Kuroshio index is positive or when the Kuroshio extension system is stabilized, you have higher sea level to the south of the Kuroshio extension jet. So the Kuroshio extension jet mean position is around 35 north. So just north of this box. So this dynamic makes sense because when the sea level is higher to the south, you have, and lower to the north, you have intensified jet, more stabilized in space, and you have intensified recirculation gyre and also eastward jet. So you can look into so these are all from models. So it turns out this dynamic property change is associated with the wind forcing associated with the Pacific decadal oscillation. And so for those of you who are not familiar with the PDO, it's just you can just think of a PDO as a intensification of the Aleutian low. So as you can see, so what's shown here is the PDO index is shown here to the right. And so you have, and then the panel in the middle shows the observed sea surface side anomaly along the 31 to 36 degree latitude north band. So this is basically the Kuroshio extension recirculation gyre, southern recirculation gyre band. And so in connection to the wind forcing is that when the PDO, for example, is positive, so when Aleutian low is intensified, you have Ackermann, so the forcing center is in Eastern Pacific. So you have Ackermann divergence, you have lower sea level in the Eastern Basin, and after these negative sea surface height anomalies propagate into the Kuroshio extension longitude in the west, you lower the sea level to the south of the Kuroshio extension jet, thereby weakening the Kuroshio extension jet and causing it becoming unstable. So you have a negative index. And the opposite, of course, is true for the when the PDO is negative, and when you have Ackermann convergence, high sea level propagating into south of the Kuroshio extension jet and stabilizing it. The important part of this realization is or introducing the Kuroshio extension index is that now you can have a dynamic framework to relate the sea surface height change or the dynamic state change with the surface wind forcing. So in the mid-latitude, we know the low frequency sea level variability is simply related to the Ackermann flux convergence divergence through this the so-called Rossby wave, baroclinic Rossby wave model. So actually you can utilize this framework, and for example, in the left, I plotted the basically using ECMWF wind and calculates convergence and then integrated along the Rossby wave characteristics, and you can derive the sea surface height variability in the western part of the basin. And so this is the model derived or wind forced sea surface height variability in the Kuroshio extension index box. So you can see there is a very good correspondence between the observed K index versus the wind forced index. And we'll come back to this point later. Now, in terms of, since this is the OASIS community, obviously we would like to connect how Kuroshio extension variability connect or interact with the overlying atmosphere. So I don't need to dwell on this. I'm sure all of you are very familiar. So for example, this Kuroshio extension, both the Kuroshio extension and the Gulf Stream are where the ocean hits the atmosphere, and also that's where the so-called storm track. So what's shown here in the lower panel is the 700 millibar V prime T prime IMS fluxes. And then probably not coincidentally, the wind stress curve line, the zero wind stress curve line signifies where the storm track axis is. And so as the Kuroshio extension system changes or fluctuates between stable and an unstable state, the sea surface height, SST gradient in the system changes significantly. So this again probably not surprising. For example, during the stable state, the zonally average SST gradient along the Kuroshio path is about let's see, 6 degrees in the wintertime, 6 degrees per 100 kilometers. Whereas in the unstable period, you have only a third of 2 degrees per 100 kilometers. So there's a huge difference in terms of the sharpness of the front, the oceanic front. So one thing we decided to do is to regress to see how the atmosphere responds to the variability of the Kuroshio extension system change. So, so this is the result showing the to the left is the QNet. So that's the turbulent heat flux regress to the Kuroshio extension index. So as you can see, essentially what happens is in the upstream Kuroshio extension region, you have a relatively reduced QNet injected because things have become stable. Whereas, so one thing I didn't show earlier is that actually when the upstream Kuroshio extension jet becomes stable, it becomes a lot more unstable downstreams, and vice versa during the unstable state. So you have a lot of mesoscale 80 fluctuations downstream, and which inject turbulent heat into the atmosphere. And the second panel here shows the V prime T prime at 850 hectopascal level. So as you can see, essentially the mean zero line, the mean position of the storm track is this zero wind stress curve line here. And when things becomes unstable in the Kuroshio extension system, you have this northward shift, poleward shift of the storm track. And for the ocean atmosphere interaction, it's the wind stress curve, or more importantly, Ekman flux convergence or Ekman pumping velocity that's relevant. So, so what's happening here is now you see this tripolar plus minus plus response. So to understand this tripolar response, it's relatively simple. So in the mean state, the subpolar gyre has a negative, have a positive Ekman pumping and a negative Ekman pumping in the subtropical gyre. So as the whole system, the wind system, shifts northward, so relatively speaking, you get this shifting positive further to the north and the negative to sort of the mid part, and then you bring relatively positive wind stress curve to the north. So you have this plus minus plus tripolar response. So it turns out this response is important for this sort of decade. So the fluctuations before 2017 has this sort of decadal fluctuations. So so as you can see, so it turns out this decadal fluctuations we believe is a consequence of this ALC feedback. So for example, let's say if you're in the intensified Kuroshio extension dynamic state, you shift the storm track northward, and you have this plus minus plus Ekman pumping response. So what's important for the Kuroshio extension, of course, is the wind anomaly, wind stress curve anomaly in this to the east. So in this east part, you have a positive wind stress curve, so which of course causes Ekman divergence, lower the sea level, and once this lower sea level propagate westward into the Kuroshio extension, it would weaken the meridional sea level difference and causing the dynamic state to unstable state. And so this process essentially has this this half cycle has this probably 5-year period, and 3 years to across the basin, and 1 year to adjust for the atmosphere, and 1 year to adjust for the oceanic part. And as a consequence, we have been arguing this sort of a decadal modulation is due to this so-called delayed negative feedback between the mid-latitude western boundary current and the overlying atmosphere. So this is what happens prior to 2017. So you have this decadal oscillation possibility related to the decadal negative feedback. Another sort of a complication is upstream. So Kuroshio extension is just east of Japan. It turns out south of Japan, an interesting phenomenon is known as large meander. So the Kuroshio Pass sort of fluctuates or vacillates between a long coast pass, so it's called a straight pass, versus a meandering pass. So it has this huge detouring pass south of Japan. And what's shown here is a time series over the past 50 years. And as you can see, the shaded region, shaded period indicate the large meander period. So it's a very chaotic and sort of appears not decadal fluctuations. It's just random fluctuation. But in any case, in the late 2017, over a long period of a straight pass, the Kuroshio south of Japan turned into a large meander pass. So as you can see, so this goes back to the prior plot I showed you. So as you can see, 2018, 19, 20, 20, 21, 22, and also last year, you just have a very, very stable Kuroshio extension state. So that nothing, not much happening essentially. And of course, upstream, you have this large meander pass. So if you look into the Kuroshio extension index, and in the past 5 years, 5 or 6 years, you have a very positive value, so indicating very stable dynamic state. And this, it turns out, has a huge consequences for Japan, because the Kuroshio extension usually, as I mentioned earlier, flows eastward at the latitude of 35 north, so this latitude. But presently, it goes all the way to close to 40 north, so which is a very, very unusual for Kuroshio extension. Of course, has a huge impact both on the climate in the northern part of Japan as well as fishery. So the question, you can ask a few questions. So one question is whether this large meander occurrence causes the Kuroshio extension to shift northward, because when you have a large meander pass, you tend to have this incident angle, which is pointing northeastward, thereby, you can possibly have a tendency to shift Kuroshio extension northward. But it turns out the answer is no. So you can do that by looking into go back to the wind force model. As you recall, this model does not know anything about upstream boundary condition. All it did is integrating the interior ocean wind forcing along the Rossby wave characteristics to the east of the Kuroshio extension, remember. So this, so the top one again shows the observed Kuroshio extension index, and the lower one shows the wind force part of the sea level changes in that box. So as you can see, regardless, even without the upstream forcing, you still have positive dynamic state, probably not to the extent of the observations, but indicating probably there is some feedback from the upstream, but overall, you still have this stable state due to the interior ocean wind forcing rather than the upstream condition. And you can look into that, actually look into the, first of all, the Ackermann pumping anomaly and also the response of the ocean. So these again are the sea level changes in the 31 to 34 degree band across the North Pacific Basin. So first of all, as you can see, there is Ekman. So this is a corresponding Ekman pumping velocity in this band as a function of time going upward and longitude from west to east. So as you can see, there's a lot of local Ekman negative, so Ekman pumping, so causing Ekman sea surface height convergence and stabilizing the Kuroshio extension, causing it to shift northward. So, so the point here, and also it turns out interesting is that PDO right now shifted from a positive phase prior to 1918 to a negative phase. So, which means in the eastern part of the Pacific, North Pacific, you have Ekman convergence, and you have a weakened Aleutiano Ekman convergence. So, so this part of the high sea level is going to propagate into the western part again. So, so because of this, we believe this stable dynamic state of the Kuroshio extension jet is going to stay for a while because you both have the local Ekman convergence as well as the remotely reinforced positive sea level income. The reverse question you can ask is whether the Kuroshio extension dynamic state change, from super positive state impacts on the large meander. That turns out to be true because if you look at so during the sunlight altimetry period, there are two events. One event occurred in 2004, which happened when the Kuroshio extension shifted from positive to a negative phase, whereas the present one shifted from a negative phase to a positive phase for the Kuroshio extension. So if you look at what happened during the 2004-2005 event, so what's shown here is the Hoff-Muller diagram of sea surface height in this dashed band. So showing early on 2004, you have everywhere you have positive sea level, and then in the early part of 2005, essentially the Kuroshio extension jet becomes unstable and creating a lot of perturbations. And these perturbations, of course, propagate westward, hitting the larger meander, causing it to shift from larger meander to a straight path. So you see this due to the downstream Kuroshio extension dynamic state change, the Kuroshio larger meander essentially disappeared due to the perturbations coming from east. On the other hand, if you look at the present case, it's just the opposite. So, so what's shown here to the right is the yearly average eddy kinetic energy in the region. So as you can see, once the Kuroshio extension position shifted northward, the kinetic energy band also shifted northward. So you can have a lot of mesoscale eddies propagating westward, but they will not cross the east ridge and perturb the upstream larger meander state. So as you can see over the actually 2003 included past 6 years, you just have a very stabilized larger meander. So, so this is my last point. So you may ask what's happening, why you have this transition sort of from a oscillatory behavior of the Kuroshio extension system to a more sort of a phase-locked stable state. It turns out, again, you can seek that from the wind forcing. So the top panel here shows the mean climatological schedule transport, and the lower panel here shows the composite of the schedule transport in the past 5 years. So, so the point is essentially the southern half of the subtropical gyre is weakened, whereas the northern half of the gyre is intensified, and subarctic gyre is also weakened. So you have this dipolar wind stress curve change. And it turns out this is a quite, so, okay, so what's shown here in the top panel is this northern part of the subtropical gyre schedule transport changes. So you can see there are a lot of fluctuations. And this is the B panel here is the southern half. However, if you take the difference, so basically you're asking what have happened if you take, you can have a lot of cases, you have the entire subtropical gyre intensifying or weakening, but the northern half intensifying and the southern half decaying scenario is actually turns out not very often. And so as you can see in the bottom, the persistent difference, the positive in the northern half, negative in the southern half, is actually relatively rare. And this, of course, changes both the dynamic state of Kuroshio, south of Japan, and also the Kuroshio extension jet. For example, if you have a weakened southern half of the subtropical gyre, so the Kuroshio becomes weaker, it tends to become sort of taking a large meander. At the same time, if the northern half of the gyre intensifies, so as far as the Kuroshio extension is concerned, it intensifies. And then, as we discussed earlier, if you have a northward shifted Kuroshio extension, then you have a less mesoscale eddy variability impinging upon the Kuroshio south of Japan. So the larger meander can sustain, and once you have a intensified Kuroshio pass, then it's sort of a facilitated northward shift. So you have this sort of a dynamic state of the two system feedback into each other in a positive way. So the takeaway is the new super stable Kuroshio extension regime is likely a result of this positive feedback between the Kuroshio extension and the Kuroshio large meander, and caused by the anomalous subgyre wind forcings. Okay, so here's all my results. I want to just conclude by a few comments that are relevant, hopefully, for the OASIS community. First, as you can see from my presentation, I think that we need continued and also mesoscale resolving sea-surface height, SST, surface wind stresses, and surface turbulent heat fluxes measurement in order to fully understand what's happening in the mid-latitude. I mean, in this case, no specific, but you can equally apply this to all other mid-latitude ocean basins. And another thing is actually, I'm sure there are questions about that. The so-called delayed negative feedback loop I mentioned in the first part of my talk is derived statistically. So clearly, I mean, we need to go beyond that. Essentially, we need to clarify the dynamics involved in this, how the atmosphere responded to the oceanic frontal scale fluctuations. And of course, I'm sure, many of you are interested in this and also are experts on this. And the last point is in terms of this coupling between the ocean and atmosphere, whether after 2018, after Kuroshio extension system becomes highly stable, whether this feedback mechanism or the feedback processes have changed. So that's something is a future research topic for us. Well, thank you very much.
Thank you so much, Bo, for the very interesting presentation. The floor is open for question. Please feel free to unmute to speak or raise your hand or put a question in the chat. So while people are thinking about questions, if I may start by asking Bo. Bo probably expect what I was going to ask because I talked to him about this before after the OST-ST meeting. So I wonder whether mesoscale current and wind coupling contribute to the observed regime shift, which is not in conflict with the feedback loop that you propose, because the wind forcing may already reflected the effect of the current and wind coupling. So the reason that I ask whether this is a potential contributor is because there have been a lot of modeling-based studies, couple model studies, for example, by Nino Renault and colleagues. And they do this couple and no couple runs. Couple as in wind and current coupling, or no wind and current coupling.
Yeah.
And then they found that the mesoscale wind and current coupling tend to stabilize the system. So, and you're talking about stable state versus an unstable state regime shift of the Kuroshio system. And in fact, exactly right. So this plot, there's a lot of small scale features in the wind stress curve as well, right? So I wonder whether that effect may contribute. I know we don't have the data to address it yet, probably. But,
yeah, excellent question. Excellent question. I've been wondering how to do a statistical, or even, I mean, obviously you could do a coupled model
right.
experiment, but how to do this no, excellent. I mean, Tony, I totally. So the question is, one thing I can think of is, through coupling, the forcing amplitude weakens, so thereby the system receive less kinetic energy from the atmosphere, thereby there's less energy injection into the oceanic system, and things becomes, the oceanic system becomes stable. And excellent. Tony, I cannot, because so right now, actually, when I talk about wind stress curve response, I'm more talking about larger scale. Yeah, so there's a tripolar, but you are absolutely right. To what extent, to what extent the energy input due to this wind current feedback that you can alter the response. I need to think about it. No, excellent question. I usually think of from the sort of heat flux point.
Understood.
But I think you're right.
Which is probably the key process. But given that this modeling study that the wind and current mesoscale coupling can actually shift the strength of the boundary current like the Kuroshio or Gulf Stream, as well as their latitudinal position. So I was just wondering whether this may have anything to do with the regime shift. But the sign may not work out. I haven't worked out a sign yet. Based on the change of the wind and the change of the EKE, whether that wind and current coupling effect in terms of sign is consistent with the feature that you are observing. I have to work it out. But it's probably something.
Well, what I presented are all large scale. So, just what happens in eastern part due to wind force and common convergence, divergence. So these are all not mesoscale that you are talking about. These are all larger scale. But I agree with you. As you very well, I didn't show eddy kinetic energy. Actually, when the dynamic system changes, there's huge amount of eddy kinetic energy change in the western part. So how that would impact on the local LC fluxes or wind current feedback is something. I think definitely.
We can.
We should
more
look
about this.
Okay. Thank you. Appreciate that.
Thanks. And Sarah have a question, and then Hilde.
Yeah, I guess I was just going to follow up on Tony's question. I'm really struck that the classic problem for Western boundary currents and models is that they don't separate at the right latitude. And here you have a regime shift where the Western boundary current has ceased to separate at the right latitude. And so if it were a model, you'd say, well, we need to improve the resolution. So it looks, by extension, you might conclude that the ocean has lost resolution, or that small scale processes have ceased to govern what's happening. Is that possible?
I'm sure the ocean doesn't know the real ocean doesn't know the grid. It's all
exactly.
No, that's Sarah. You know very well. You and I were together at Woods 30 some years ago. I never seen. I showed a picture of the Kuroshio extension. I worked on the Kuroshio extension for 30 some years. I never seen a Kuroshio extension extends all the way to 40 degrees north. So I Yeah, I don't think the ocean, suddenly feels, the grid becomes finer. I think it's still the wind. Ultimately, it is a western boundary current. So the more subtle question is, what kind of wind forcing are we talking? I mean, there are a lot of people talking about the northward migration of the Hadley circulation. Is that a part of that? And why? Because we know that migration has happened for a while. Why suddenly, in the North Pacific, 2018 becomes a sort of important year. So these are the questions. So as again, this analysis hasn't kind of delved into that. Is how I only mentioned, it's very the fluctuations are very special, sort of a thought, because usually you think, the gyre spin up, so the whole wind gyre spin up, but it's not. It's actually just more than half of the gyre spins up, where the southern part drops. So maybe that's part of the Hadley circulation northward expansion. Is it just, the wind forcing, just the northern part shifted and intensified, the southern part changed. So I think to answer your question, I still feel it is the wind, but why, in this particular period, that wind takes that particular form of fluctuations is something I think, yeah, we need to find out, definitely.
Thanks.
Hilde, you have a question? I see.
Yeah, so hi, Paul.
Hi.
How are you?
Very
I
good.
just want to follow up with Tony's question about this current wind mesoscale feedback. That you see
Absolutely.
a lot of mesoscale structures here. And I think, those relative wind or eddy killing thing that people talk about, they apply to all those different current systems and show the kinetic energy reduces and gyre circulations stabilized and things like that. It's really interesting. It doesn't seem to be the case for this large meander, though. So we have done this. There's a student in Korea, Hajun Song student, and I've been working with her. She's running this, usual run model with couple run without surface current in the stress formulation, and we don't see any shift in the large meander. I mean, we once say large meander in the Kuroshio system is, internally driven dynamics, right? So like energy conversion processes, in which case we expect sort of, if you change the stress, you change baroclinic instability and conversion of this energy from potential to kinetic energy. You expect the large meander to behave something like other current systems that you see in the Gulf Stream or Kuroshio, downstream, where it changes, path and meander and intensity, things like that. But very strangely, the large meander didn't change at all. And I thought it was a very interesting idea. I don't know why. So I just wanted to throw out there that there seems some maybe other factors, right? Topography and other feature may be more constrained more strongly this path of the currents in the south of Japan, right, of the Kuroshio.
Yeah.
Than other parts of the current system.
No, that's a huge question. I mean, I presented this time series. If you look at this time series, it's just totally, at least appears not to be connected to. Usually, you think of, well, wind, where you have you can have PDO, you can also remotely forced wind, and doesn't seem to be related to those. One thing I don't want, yeah, well, one study we did was it seems to me, seems to us, there's a so this is a very high kinetic energy domain, and in the North Pacific, actually, there's a second high eddy kinetic energy band called a subtropical countercurrent region. So this is a band around 20 to 25 north, so between Taiwan latitude and Hawaii latitude. So in that band, because the Ekman convergence in the surface wind, you have a lot of surface barochronicity, and it has a lot of eddy kinetic energy changing. So it turns out you're absolutely right. It's looks like related to a lot of eddy generation here. So of course, when you have a subtropical countercurrent eddy fluctuations, those eddies kind of propagate westward, and when it hit western boundary, they are being advected downstream. So those eddies having a lot to do with the formation and the duration of the large meander. So it is true what happens in the Kuroshio extension, Kuroshio, south of Japan, and Kuroshio extension, east of Japan, are very different.
Mm-hmm.
And that's probably true, yeah. The Gulf Stream variability in the mid-Atlantic bight, and when it separates from Cape Hatteras, probably behave quite differently. One is more constrained by the local dynamics. One is more sort of in open ocean, subject to interior wind forcing. But right now, well, to be honest with you, Hyode, we don't know fully well what really, causes this larger meander on a decadal and a longer time scale. Yeah, so that's another
certainly
topic.
The relative wind stress effect doesn't seem to be the candidate. So that's one, good that we rule out one factor.
You mentioned your colleague in South Korea. Actually, Axel Timmerman came to Hawaii during the winter break, and Nicholas, Axel, and I, we got together and discussed about that. So it looks like it's quite interesting. They have two high resolution coupled model. One, has a wonderful large meander, one doesn't. So we talked about it, and we're hoping that colleague will work, the specifics out.
Yeah, we should be looking at their runs.
Yeah.
Thank you.
Thank you.
Anyone else have questions? If I may ask another question, Bo?
Absolutely.
Or to Hyode or people who are familiar with the modeling aspect of it, how well do the models, force or couple, represent kind of the regime change of the Gulf Stream, the Kuroshio? For example, if we use the index that you develop, do they show such a dramatic shift?
So
doesn't have to be the right timing.
No. Yeah, I understand. So this two. So again, going back to what we have just discussed. So again, Kuroshio large meander and the Kuroshio extension are two separate things. Yeah. So the answer to your question, well, let's take. I'm most familiar with the so-called OFAS, the jamstack high resolution. So that's a 1/10 of a degree global model, and so that model does a wonderful job in terms of Kuroshio extension variability.
Got it.
So decadal variability. So again, going back, you may say why? Well, because it's largely wind forcing to the extent. So it's a wind force model. So the force OGCM. So in that respect, it's not surprising. Yeah, you have the correct wind, and then it drives the correct fluctuations. But the model, the OFAS, does a horrible job about the larger meander. It not only doesn't simulate what's being observed, it also has basically it tends to be in a large meander state, not mostly in the straight path. So this goes back to Nicholas Schneider and I. Nicholas for a while have been analyzing that model output. So what the conclusion we reached was it's just a mesoscale 80 resolving. It does not resolve summer-scale variability. So as a consequence, there's a lot of balanced motion or mesoscale 80 variability in the south of Japan, which cannot be dissipated in the model. So as a consequence, you always need to have variability or large meander try to kill the. So I think that's so in a sense we kind of know, but again, going back to Hyode's question, let's say if you moved from mesoscale to sub-mesoscale, whether well right now we don't have a global basin scale, sub-mesoscale resolving model, so we cannot say the outcome. But hopefully, by moving into the higher resolution, the large meander issue can also be addressed. Yes.
So following up on Hyode's comment about the potential contribution of the bottom drag, I wonder whether there have been any published studies discussing the sensitivity of whether you have the large meander or not, depending on the bottom drag.
Even bottom topography, yeah.
Yeah.
Bottom
drag or bottom topography?
Oh, bottom drag. I'm not so sure about the bottom drag. They are studied. So there's a ridge system here called Easy Ridge here. So one idea is, let's say, when you have a relatively weak Kuroshio inflow. So, so as you can see, then it tends to, you can have a, let's say, you have eastward jet and you have westward Rossby waves. So potentially you can have a station what's that word? Trapped Rossby waves. So essentially, yeah. So I think, and also because you have a topographic system here, so you can trap the large meander. But that, yeah, it doesn't. So there are studies along that lines, but because then you say, well, let's compare with the real wind. Yeah, so look like, you argue when wind forcing is weak, then the inflow is weak, and then you tend to have large demand. That doesn't seem to be the case observationally, because wind forcing is a lot more variable than the observed large meander event. So I think that also still under debate.
Got it. Thank you. Any further questions for Bo? Sarah?
I guess I wanted to just ask the sort of Oasis type question, shifting the Kuroshio extension, shifting the temperature gradient must have a big impact on sort of the frontal scale air-sea heat fluxes. So you mentioned implications for Japan in terms of fisheries and sort of maritime issues, but there must be a weather issue as well. Has anybody looked into that?
Yeah, so I didn't do it. I wish I have that figure with me. So absolutely. So the question is, what's the downstream? I mean, focused on the local impact. As you can see here, so when the whole system shifts northward, so this study by Ma et al., I think it's 2015 in the scientific report, they used trim data and looked into the rainfall over the entire North Pacific as well as northeast of U.S. continent. And what they found was, exactly like this. So they composited when the Kuroshio extension is in the stable minus unstable states. So these are decadal composite. And so what they found is exactly, so as you can see, the curl is positive. So positive in the so in the lower atmospheric boundary, you have convergence, thereby you have more rainfall. So this enhanced rainfall, of course, not only occurs over the ocean, it also over the northeast U.S. So they were arguing the dynamic state change in the Kuroshio extension also impacts on that. I wish I have that figure with me. Yeah, so that's one. So that's actually something, would be interesting now, since you have in a super stable state, and the whole system really shift northward, where the similar kind of rainfall change is seen in the northeast U.S. Yeah, it's something definitely worth checking into.
Thanks.
Thank you.
So Megan has a question, and then David Trossman also have some comments that maybe they can ask those questions.
I cannot read. Oh, Megan, go ahead.
Yeah.
Hi. I was just wondering if there's something funny going on in the Gulf Stream as well.
Do we have a Gulf Stream expert here? Looks like, well, my personal I haven't worked on Tony, you worked on the Gulf Stream before. Maybe you have a
not for the 2018. I already.
Megan, sorry, I cannot answer that question. Yeah, somebody should definitely look into. You have the data over the past 30 years. Very nice sea surface height measurements, and if everything is due to the hardware circulation expansion, maybe you're right. Probably something strange should also occur in the North Atlantic. So maybe my talk can inspire a colleague to look into that.
Yeah. So the Gulf Stream.
Megan, you are muted. We cannot hear you.
Right, Megan.
I love Sarah's hypothesis that the model, the Earth model, is losing its resolution. But okay, anyway, go on.
Thank you.
Yeah, the Gulf Stream definitely does not have this kind of large meander that extends so far up. But in terms of the lateral shift of the Gulf Stream path and what drives it, and there's still a lot of debate whether it's just forced by the atmosphere or whether there's an internal stability involved in that as well. I remember when I was doing my thesis, and after I finished my thesis, there are a lot of work by Michael Gill and others using idealized models and looking at bimodal distribution and in the Gulf Stream system and the subtropical gyre. Haven't followed that line of study for a while. Maybe some other people might be more familiar with that.
The last study, actually, okay, sorry.
Yeah, go ahead.
The one study I do remember is from Magdalena from Woods Hole, but it was published maybe prior to COVID. And her my recollection was, it doesn't really have this decadal modulation. It may have a lot of fluctuations, but on a somewhat shorter time scale. So maybe, I mean, this goes back, all the way to this first slide I have here. And so I think, really the difference between the North Atlantic and North Pacific is the width. This is probably, it's a North Atlantic basin size is probably half of the North Pacific. As a consequence, you always have Rossby wave response and so on, but the accumulative effect, the reinforced accumulative effect in the Gulf Stream, I believe, would be smaller than the North Pacific. So this is wide enough so that the reinforcing can accumulate, and then you can generate the lower frequency variability. So I think this probably difference in IMS, decadal IMS variability is probably due to the basin size.
Yeah, thank you. So David Trostman just put in a chat a couple of references related to my questions. He was responding to my question about the potential role of bottom drag on Kuroshio positions. So there are a few papers there. By Trostman et al.
I'll just add that I remember that the Kuroshio region was the most sensitive to putting in different parameterizations of bottom and wave drag of the ocean. For SSH variability and Kuroshio position out of any intensified current. So, and I never understood why, and I've never stayed in a job for long enough to be thorough. So that's a follow-up investigation someone else could do.
Interesting.
Yeah,
definitely look into it. Yeah.
That might also bring up an interesting question of to what extent that the prescribed bottom drag is compensating for the potential role of the drag at the surface, namely the mesoscale airsea interaction. So which has similar effect. Think of it as kind of a surface drag and bottom drag. And you could do it either way in the model to either stabilize the current system or to make it more unstable, or which has consequences on the latitude position of the Kuroshio or Gulf Stream because of the eddy mean flow interaction. So I think that might still be a kind of open question. So what is the correct magnitude of the bottom drag versus the surface drag or airsea interaction? But may not be in the context of the large meander, as Bo and Hilde said. Yeah. Okay. Any further comment or question to Bo? Okay, if not, thank you very much again, Bo, especially for giving up so early to give the presentation. Yeah, appreciate it.
Thank you very much to you all, and for your interest and participation. Yeah, thank you.
Take
Thanks.
care, everyone. Bye-bye.
Bye.